Hello, I welcome you all to your own channel MSK Learnium. If you remember, in last class we have discussed about the simple stress and strain. It means that we simply find, that means we see what is a stress, what is a strain, Hooke's law, and some elastic constant, that is modulus of elasticity, modulus of rigidity, etc. Now in this class we will discuss that the next elastic constant, which is the Poisson ratio. So Poisson ratio we are denoting by letter mu or m, that you can express as mu or you can say the 1 by m. This is the notation for your Poisson ratio. So Poisson ratio is what? That lateral strain to the longitudinal strain. It means that if you remember the previous video, that we have some bar is there, that right, whose length is L. Let's say this length of the bar is L. Is it or not? Now what we are doing, that this is the longitudinal dimension and this is the lateral dimension. This is the lateral dimension, let's say B, that is width of this element. So we are pulling this body with a magnitude of P. So we are applying the tensile load. So when you apply the load, what will happen? That there is a longitudinal dimension will increase but the lateral dimension will decrease. It means at a time two strain will act, that is one along the longitudinal strain and one is the lateral strain. So if you see that as you apply the load along the axis of the length, means along the longitudinal axis, so the longitudinal dimension is increased, but at the same time the lateral dimension is decreases. It means that along the longitudinal axis we have a longitudinal strain and along the lateral axis we have a lateral strain. So you can find the longitudinal and lateral strain are opposite to each other. So longitudinal strain is what? The change in length by original length, or you can say the longitudinal change in longitudinal dimension by original dimension. Lateral strain is what? The change in lateral dimension by original dimension. So now we can say that Poisson ratio is the ratio of the lateral strain to the longitudinal strain. So you can write it here, that Poisson ratio is a ratio of lateral strain to the longitudinal strain, okay, to the longitudinal strain. So here you can say that is Poisson ratio is what? Poisson ratio either you can denote it mu or 1 by m. So I am using the mu. So Poisson ratio is what? That you can say the lateral strain upon longitudinal strain, right? So when you cross multiply, that the lateral and longitudinal strain are opposite to each other. Here the longitudinal dimension is increasing but the lateral dimension is decreasing. So you can say here that the lateral strain is equal to minus mu times of longitudinal strain, minus mu times of longitudinal what? Strain, right, by into longitudinal strain. So this is your relation between lateral strain, Poisson ratio and the longitudinal strain. So lateral strain is minus mu times of longitudinal strain, right? It means that lateral and longitudinal strain are opposite to each other. Some material we will see and then we see that what is the Poisson ratio for that. So suppose you have a concrete, that Poisson ratio for concrete, that is Poisson ratio mu is equal to 0.15. For concrete the Poisson ratio is 0.15. Next you have a for cork. The Poisson ratio mu is equal to, you can say it will be 0, right? Third, you have a rubber. For rubber, the Poisson ratio mu is equal to, you have a 0.5. Fourth one, you have a isotropic material. Isotropic material is one whose Young's modulus are same. Isotropic materials. For isotropic materials, mu is equal to 0.25, right? So you have a 4 for concrete, the Poisson ratio will be 0.15. For cork, the Poisson ratio is 0. For rubber, Poisson ratio is 0.5, and for isotropic material, the Poisson ratio is 0.25. Now we will see the stress-strain relation in 2 dimension and in 3 dimension. So first of all, we will see the relation for 2 dimension, that you can make a subheading, that is stress-strain relation for 2 dimension body, right? So here you can write that relation between, it's better you can write relationship between what? Stress and strain. So the relationship between stress and strain is this one for 2 dimension, right? In 2 dimension, that it's better you can write in 2 dimension, that is 2D, is it or not? So relationship between stress and strain in 2 dimensions. So for that, what I'll do, that let's say one section is there, right? So this is the x-axis and this is the y-axis. On x-axis, the stress is induced, which we consider as a sigma 1, right? And on y-axis, the stress is induced, which is the sigma 2. So these are the tensile stress. Why? Because you can see it is in the pulling in nature, right? So sigma 1 and sigma 2 is the stress on x-axis and y-axis. Let's say that whatever the body we have considered or the section we have chosen, whose Young's modulus is E, right? So now you can say let sigma 1 is a normal stress in what? In x direction, and we can say sigma 2 is the normal stress in y direction, right? Sigma 2 is the normal stress in y direction. So we can say that if you look at here, that sigma 1, when you consider the sigma 1, that is stress along x-axis. So you are pulling, means it is tensile stress. So when the stress is induced along x-axis, it means that along x-axis the length will increase, right? But on y-axis the length is the length will be decrease. That means the longitudinal dimension will increase because of this sigma 1, and the lateral dimension will decrease. It means that because of this sigma 1, the 2 stresses will act. That is, the strain will produce in x-axis as well as on y-axis. So on x-axis the strain is the positive, that is longitudinal strain, and on y-axis the strain will be the lateral strain. That means both are the opposite to each other. So first of all, we can say that sigma 1, you can write sigma 1 will produce strain in x direction, also in y direction, is it or not? Similarly, you can say the so in x direction what will happen? In x direction the strain will be longitudinal, and in y direction it will be the lateral. So you can say in x direction, that a strain will be what? Longitudinal. Will be longitudinal. Okay, and in y direction, the strain is that okay, in x direction strain will be longitudinal, and its magnitude is sigma 1 by capital E. That is the stress by strain. Young's modulus is the strain from the Hooke's law. And in y direction, the strain is, in y direction a strain will be what? Lateral. So from Poisson ratio, if you see that, what is Poisson ratio? That means lateral dimension, lateral strain by longitudinal strain. It means the lateral strain, you can say lateral strain is equal to minus mu times of longitudinal, and because of the sigma 1, the longitudinal strain is sigma 1 by E. So this is the lateral strain because of this sigma 1. Similarly, you can move to the y axis, that you consider sigma 2. So in the same way, the sigma 2 will produce the strain in x direction as well as in y direction. But if you look at, the sigma 2 is on the y axis. So when the sigma 2 will consider, then because of this sigma 2, on y axis we have a longitudinal strain, but on the x axis there is a lateral strain. Means its length, the longitudinal axis length will be increased, right? So that magnitude, the longitudinal strain will be for sigma 2 is sigma 2 by E, and the lateral is minus mu times of sigma 2 by E. So same thing you can repeat, that you can write it here, that sigma 2, you can say like this, similarly sigma 2 will produce a strain in x and y. Sigma 2 will produce a strain in x and y direction, right? So you can say the in x direction the strain means because of this sigma 2, in y x direction a strain will be, you can write a strain will be lateral, no problem, lateral, right? But in y direction it will be the longitudinal, right? And in y direction, in y, and what is this value? Okay, later on y direction a strain will be what? Longitudinal, will be longitudinal, right? And its magnitude is nothing but that is sigma 2 by E, right? Sigma 2 by E. So its lateral strain is what? Minus mu times of sigma 2 by E. So it means that because of that sigma 1 and sigma 2 on x and y axis, we got the 2 strain. That when we consider the sigma 1, the strain on x axis is longitudinal and a strain on y axis is lateral. Similarly, when we consider the sigma 2, the strain on y axis is longitudinal and a strain on x axis is lateral. So let's say that what is the total strain on x and y, right? So for that you can say that here, yes, you can say that let E1 is equal to total strain in x direction, that total strain in x direction, right? And E2 is equal to total strain in y direction, right? So if I say the total strain in x direction is what? The strain because of that longitudinal strain because of sigma 1 and the lateral strain because of the sigma 2. So you can say E1 is equal to, that is a longitudinal, that is sigma 1 by E, and lateral strain because of the sigma 2, which is nothing but the mu times of sigma 2 by E, right? This is the strain in x direction. Similarly, if you have to calculate the strain in y direction, means that longitudinal strain because of the sigma 2 and the lateral strain because of the sigma 1. So E2 is equal to total strain in y direction, you can say sigma 2 by E minus mu times of sigma 1 by E. So this is what we got, the relation between stress and strain in 2-dimension element or 2-dimension body. Now we can see the stress and strain relation in 3-dimensional body. So let's say that in same fashion you can say that you can make a subheading first, that for stress strain relation for 3-dimension system. So you can write that stress strain relation for what? 3-dimension system, right? So this is your relation. So let's draw one 3-dimensional body or a system. So here I am drawing one cuboid. Okay. So this is your x-axis, y-axis, and this is your z-axis. Is it or not? Now, so on x-axis, that this is a parallel to the x-axis, that is a stress in sigma 1. This is parallel to y-axis, it will be like this, that is a stress on y-axis is sigma 2, and this will be the like this, that is a stress on z-axis is sigma 3. Sorry, this is x, this is your y, and this is the z. So on x-axis the stress is sigma 1, on y-axis sigma 2, and z-axis it is sigma 3. So it means that because of the sigma 1, the strain on x-axis, y-axis, as well as on z-axis. But if you see that this is the x-axis, is it or not? This is the x-axis. It means that one tensile stress is this side also. So when this tensile stress will act on the x-axis, it means its longitudinal dimension will increase. But at the same time, the y coordinate, y direction, the dimension along the y-axis and the dimension along the z-axis is going to be compressed. It means along x-axis we'll get the longitudinal strain because of the sigma 1, but on y-axis and z-axis we'll get the lateral strain. Similarly, when you take into consider the sigma 2, which is acting on the y-axis, so this is your y, this is your y, right? So when the stress will act on the sigma 2, that means on y-axis. So on y-axis there is a longitudinal strain, but on x and z there is a lateral strain. Similarly, when you take into this consideration, that is z, right? You can see the movement of my hand. This is the z, right? So it is like this. So when it is stress will consider on z-axis, it means on z-axis the strain will be longitudinal, but on x and y the strain will be lateral, right? So similarly, you can say that one statement I'll write, and then you have to write down for the similar. That is, not let the sigma 1 will produce a strain in x, y, z direction. Means in all 3 dimensions the strain will produce because of the sigma 1, but sigma 1 will produce strain on x-axis, is longitudinal, right? But on y and z lateral, right? But on y and z it will be the lateral strain. So it means that sigma 1 will produce the strain on x, y as well as on z. But on x axis it will be your positive, that is lateral longitudinal, and on y and z it will be the lateral. So then you can say whatever we have discussed. So you can say here it means that is in x axis because of this sigma 1 in x axis due to sigma 1, that strain is equal to what? Longitudinal, which is sigma 1 by E. In y axis it is minus mu times of sigma 1 by E, right? And in z axis it is also minus mu times of sigma 1 by E. Okay, now if you consider sigma 2, that will give you the strain on y axis, it is longitudinal, and x and z will be lateral. So similarly you can write similarly due to sigma 2, that is strain in y axis is equal to what? That is sigma 2 by E, that is longitudinal, but in x axis it is what? Minus mu times of sigma 2 by E, and on z axis it is the minus mu times of sigma 2 by E, right? Similarly, when we consider the sigma 3, you can say similarly due to what? Sigma 3. So due to sigma 3, that z axis strain in z axis is equal to sigma 3 by E, right? And in x axis it is minus mu times of sigma 3 by E, and in y axis it is also lateral, that is minus mu times of sigma 3 by E. So if I say that E1, E2, E3 is the strain on x, y and z, right? So the total strain in x, total strain in y and total strain in z we can find, right? So now you can write that let E1, E2, E3 are strain on x axis, x, y and z axis, right? X, y and z. So we can say E1 is equal to what? E1 is equal to, that is sigma 1 by E due to stress on sigma 1, and x axis due to sigma 2 is what? Minus mu times of sigma 2 by E minus mu times of sigma 3 by E, right? Similarly, if I write for E2, right? So E2 is what? Sigma 2 by E, because of this sigma 2 strain on y axis is a longitudinal and the x and z will be lateral. So next is what? That is minus mu times of sigma 1 by E minus mu times of sigma 3 by E. Okay, now then finally E3 is equal to what? That is sigma 3 by E minus mu times of sigma 1 by E minus mu times of sigma 2 by E. So these are the strain we got on x, y and z axis in 3-dimensional system, right? Now then we move to the next topic, that is analysis of varying cross section, right? Yes, so you can make a subheading, that analysis of varying cross section. That is small topic is there, fast you can write analysis of varying cross section. It means what? that one section you have taken into consideration whose section is varied across the length. So how the section looks like we will draw here, right? So let's say your section is like this. It's actually red color is not visible on camera, so it seems like blur, right? So this is one section we have taken into consideration. The next section is like this, right? And the next section is like this. If you look at the diameter of the section is changes. Let's say this diameter of the section is D1. Let's say this is 1, this is your D2, and this is the D3. Means we are considering that the cross sectional section is there, right? The length of this is, you can consider it as a L3. This is your L2. Don't mind that I'm coming from back to final to initial, right? So this is your L1. Is it or not? Sorry, this is the L1, right? And the load is acting, we can say the tensile load is acting of having equal magnitude but in opposite direction of P. And these section, this section 1, 2 and 3 are the homogeneous, right? It means it is made up of the same material. So as this is made up of the same material, so Young's modulus for this section 1, Young's modulus for section 2 and Young's modulus for section 3 will be same. So here you can write some point that let a varying cross section, okay, L1, L2, L3 are the length, right? D1, D2, D3 are the diameters of section 1, 2 and 3, right? And P is a load applied. Which type of load? Tensile load. And you can say the E1 is equal to E2 is equal to E3, that is equal to E. Why? Because it is homogeneous. Is a Young's modulus. Young's modulus of that section, right? Of that section. Then what we have to do, that we need to analyze the varying cross section. So each body we can see that, or you can say also that A1, A2 and A3 are cross sectional area of 1, 2 and 3. So first of all we can find the stress in section 1, stress in section 2, stress in section 3. So this is your section 1, 2 and 3, right? So now you can say here that stress in element 1. Stress is what? Load by area, that we can say sigma 1 is equal to, load is uniform, P by A1. Similarly you can say stress in section element 2 is what? Sigma 2 is equal to P by A2, and sigma 3 is equal to P by A3. These are the stress we calculated. Now we can say the strain. Then you can say strain in element 1 is E1, right? So a strain in element 1 is equal to E1, and that is what? E1 is equal to sigma 1 by E, right? So sigma 1 is what? P by A1 we can say. And further, okay, sorry, this next. So now you can say that E1, E2, E3 we calculated. Okay, only E1 we calculated, right? So similarly you can say, just wait, just hold on, that is a strain in element, where? Element 2, that is E2 is equal to what? Sigma 2 by E, and E3 is equal to sigma 3 by E, that is a strain in element 3. So now that is E1, if I write down, E1 is equal to what? E1 is equal to, if I substitute sigma 1 is equal to P by A1, so this will be P1 by P by A1E, right? And E2 is equal to P by A2E, that is P1 is, it's nothing, P only, right? So E3 is equal to P by A3E. This is the strain we got from the relation which we generated for stress, right? So simply we substituted the stress, sigma 2 value is equal to what? P by A2, so it become P by A2E, it become P by A3, is it or not? Now we can say further, you know, strain is equal to what? Strain in the element is change in length by original length, that is delta L1 by L1, right? So if I say that how much, because of this, as the load is act on the section, so how much elongation will takes place, right? The total elongation in a varying section is what? Elongation in this, and elongation in this, there is the sum. So that elongation in each cross section we are going to find. So delta L1 is equal to, can you write EL1, right? And this delta L1 is equal to, E1 is what? P by this, so you can say the PL1 by A1E. Similarly, you can say delta L2 is equal to what? PL2 by A2E, okay? And delta L3 is equal to, you can say what? PL3 by A3E, right now? Now, so total elongation, you can say total elongation. Elongation I am talking, why? Because this is, you are applying the tensile. If you compressive, you can say the total compression, right? Elongation, total elongation in varying section, in varying section. What is the total elongation? That delta L is equal to delta L1 plus delta L2 plus delta L3. When you substitute this, you can see P by E is common everywhere, P by E, P by E, P by E. So we can get common that P by E into L1 by A1 plus L2 by A2 plus L3 by A3. This is the total elongation in a varying cross section you got, okay? This is the total elongation in a varying cross section. This is the formula how we get the elongation in a varying cross section. So we'll do one numerical problem, that is small problem we have taken for today class, right? So that problem is on your screen. Please very fast you write that the ultimate stress for a hollow steel column which carries an axial load of 1.9 meganewton is 480 Newton per mm square. If the external diameter of the column is 200 mm, determine the internal diameter, take factor of safety as 4. So solution, we can say that you have a hollow column is there. So column is a vertical section which is subjected to the compressive stress. So let's say this is your hollow column. This is your hollow, right? This is the internal diameter and this is the external diameter, right? So this is your D naught, okay, and this is the DI, internal diameter, right now. So now what are the given data is given to you, that is axial load is 1.9 meganewton. Axial means what? Along the axis, right? So let's say that given data that P is equal to 1.9 mega Newton. Mega means what? That 1.9 into 10 to the power of 6 Newton, right? And that because of this axial load, the stress which induced, that is the ultimate stress, is 480 Newton per mm square, right? So ultimate stress I am denoting with sigma u, which is the 480 Newton per mm square, right? The external diameter is given, that D naught is given to you 200 mm, right? So the D naught is equal to 200 mm, right? Factor of safety, that is Fs, is given 4. You need to find out the internal diameter is equal to what. So whenever the factor of safety is given, ultimate stress is given, and the column is subjected to the axial load. When the column is subjected to the axial load, it means that because of this load, the stress will be induced on the column. That stress we call it as a working or permissible stress. So first of all, we will find out what is the permissible stress for the body, means for the given section, right? So you know that factor of safety is equal to what? Ultimate stress by working stress, or permissible or design stress you can say. Let's say I am writing the working stress, means what? At the stress at which the column is in working condition, right? So we need to find out the working stress. So you can say the working stress is equal to what? Cross multiply, you'll get the ultimate stress by factor of safety, right? Now, so working stress is what? That is ultimate is 480 by 4. It means you got 120 Newton per mm square. This is your ultimate stress. So ultimate stress we calculated, which is the I'm very sorry, this is the working stress. I'm extremely sorry, that is the working stress, right? So working stress we calculated, which is the 120 Newton per mm square, right? Now then we can say stress is equal to what? Load by area, is it or not? So you can simply you can write, yes, here we take the page, that is stress is equal to what? That general we are saying that stress is equal to what? That stress is equal to, means working stress, you can say working load by area, right? Now that is load by area. So it's better you can write that working stress is equal to working load, right? Working load. Now it's very clear, that picture is very clear. Working load by area means what? That working load is given 1.9 meganewton, means because of this 1.9 meganewton, whatever the stress is induced, that stress we call it as a working stress, which we calculated. So working stress is what? How much? 120 Newton per mm square. Working load is given 1.9 into 10 to the power of 6 by area of the column, right? So area of the column we calculated is equal to what? 1.9 into 10 to the power of 6 by 120, is it right? Now, so area of the column is what? Column is hollow, so area of the column we can say pi by 4 d naught square minus di square, is it right? Is 1.9 into 10 to the power of 6 by 120. So cross multiply, you can say this will be d naught square minus di square is equal to 1.9 into 4 by into 10 to the power of 6 for this one, into 120 into pi. This is or not right? So d naught square is this one, so it will come to this side. So di square is equal to, you can say d naught square minus 1.9 into 10 to the power of 6 into 4 by 120 into pi. This calculation simply. So di is equal to what? Root over of, simply you can substitute 200 square minus 1.9 into 10 to the power of 6 into 4 by 120 into pi. So di you got, right? So di is equal to what? 140.85 millimeter. So this is your answer. This type of problem is very fundamental problem, right? So this is what we have discussed today. In next class we will see the stress analysis in composite body. Also we will see the thermal stress and thermal stress analysis in a composite body. So this is all about the today class. Thank you.